Hello friends, welcome to Dev's Coding Hub. Today we are going to start a new playlist based on number systems. So let us start the number system series without wasting any time. Let us move to the first video of this series. Let us first know what number is. A number is a mathematical object used to count, measure, and label. Basically, a number is a count or measurement that is really an idea in our minds. Let us see one example. Look at this monkey. He has some bananas in his mind. So, how do we express this some bananas? So, for this, we have to know about numerals. So, let us move to the next slide where we will know about numerals. We already know what number is, but how do we represent a number? For being manipulated, individual numbers need to be represented by symbols or numerals. A numeral is a symbol or name that stands for a number. As for example, 3, 49, 12, etc. As only a small number of symbols can be memorized, basic numerals are commonly organized in a numeral system, which is an organized way to represent any number. So let us know what is a digit. A digit is a single symbol used to make numerals. As for example, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are the 10 digits we use in everyday numerals. So it is the most commonly used set of digits that we use to form numerals. First example is the numeral 4. It is made up of only one digit, that is 4. So a single digit can also be a numeral. Example 2. The numeral 407 is made up of 3 digits, 4, 0 and 7. So multiple digits can also be a numeral. So let us know, we know already, but let us understand what is the most commonly used numeral system. The most common numeral system is the Hindu-Arabic numeral system, which allows representing any number by a combination of 10 basic symbols from 0 to 9, and all the symbols are called digits. We have already discussed. In addition to their use in counting and measuring, numerals are often used for labels. As with telephone numbers are nothing but labels. For ordering also, as with serial numbers, and for codes, as with ISBN numbers given to book. ISBN stands for International Standard Book Numbers. So what do we call number or numeral? Generally we say number when we really should say numeral. But frankly speaking, it does not really matter if we do that, because the other people still be able to understand us. So whether we use the term number or numeral is not very much difference. But when we use the term digit, this is different. We should always use digit only when talking about the individual symbols that make up numerals. In common usage, a numeral is not clearly distinguished from the number that it represents. Now let us come to the main topic, number system. What is a number system? A number system is defined as a system to represent or express numbers. It is the mathematical notation for representing numbers of a given set by using digits or other symbols in a consistent manner. Number system thus deals with the representation of numbers. Types of number systems. So before we go into different types of number system, let me clarify that in this tutorial I am not going to discuss different types of numbers, natural numbers, integers, rational numbers, real numbers, or as such. Rather, in the context of computer science or computers, I am going to focus on the types of number system, and they are the decimal number system, the binary number system, the octal number system, and the hexadecimal number system. Now let us discuss the concept of positional number system, because it will be helpful in understanding the four number systems I have discussed. A positional number system is a system for representing of numbers by an ordered set of numerals oblique symbols called digits, in which the value of numeral or symbols depends upon its position. So in which position a digit is occurring, according to that its value is determined. Example, decimal system, binary system, octal system, hexadecimal system, and so on. Another number system is there, which is called the non-positional number system. A non-positional number system is a system for representing of numbers where each symbol represents the same value regardless of its position. In non-positional number system, each symbol represents a number with its own place value. Example, Roman number system, where 1 is used for Arabic 1, 2 lines or 2 eyes used for 2, and V or a symbol like V is used for representing 5. So before we go to number systems, we must know what is radix of a number system. Radix is a term used to describe the number of digits utilized in a positional number system. For example, in the decimal number system, there is a total of 10 digits used, which is 0 to 9. Therefore, its radix is 10. Whereas in binary number system, there is a total of 2 digits used, 0 and 1. So, its radix is 2. So, radix is also commonly known as base of the number system. So whether we say radix or base of the number system, both are same. So how numbers are generated in sequence in a number system, or how numbers are continuously generated. The radix or a base is the most important aspect while generating numbers in a number system. Take the example of the most common decimal system, which is a base 10 system, as because we have 10 digits in this system. Here, once we complete using the 10 digits as a single digit numbers, we roll over to the next digit's place. Let us see how it happens. We are starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And as we have completed 0 to 9, we have completed or used all the possible digits from 0 to 9. Now there is no more digit. So for this, again, this first place or unit place will be reset to 0. So we have completed one cycle of the number system. So we get the number 0 in unit place, and as we have completed one cycle of the number system, we are putting 1 in front of 0, that is 10. So let us again see, if we count from 10, after that what is changing? The 10th place is stagnant, fixed. What is changing is the unit place. 11, 12, 13, 14, 15, 16, 17, 18, 19. As we have completed one more cycle of the number system, so we'll again reset the 9 to 0. And as because one more cycle is completed, we will add 1 to this 10 plus 1. Now it will become 20. This is how numbers are generated in any number system, which is positional. So let us see or go through a quick reference of number system. So the 4 number systems which are popular when you work with the computer, I am just depicting those. The first number system is the decimal number system. Its radix or base is 10, as because the number of digits used are 10. It is 0 to 9. Let us have some example of numbers in this system. If I write 469, it is a valid number in decimal system, as because 4 is there in this list, 6 is also there in this list of digits, and 9 is also there. Similarly, 827 is also a valid number in decimal system. The second number system is binary, and the base or radix of this system is 2. So we are not going to use 10 digits, we are only going to use 2 digits, and these are 0 and 1. So let us see some example of binary numbers. 101, 110. These are examples of binary numbers, as because these numbers are formed with either 0 or 1 or both, a combination of both. Third number system is the octal number system, as because the base of the octal system or the radix of the octal system is 8. It supports 7 plus 1, 8 digits. So as we can say, as because only 8 digits 0 to 7 are represented in octal, so the base of the octal is 8. Now some valid numbers in octal could be 463, 127, etc. Fourth number system we are going to discuss is hexadecimal. Decimal stands for 10, deca decimal stands for 10, and 6, hexagon is 6 sides. Okay, so hexadecimal means 10 plus 6, 16 base. In this system we have 0 to 9, and then 10 is represented by A, as because a digit cannot be combination of two digits. 10 is a combination of 1 and 0, so we cannot represent 1 0, which is 10, as digits. So instead of 10 we are writing A, for 11 we are writing B, for 12 we are writing C, for 13 we are writing D, for 14 we are writing E, and for 15 we are writing F. So 4D, ABC are all valid numbers in hexadecimal. So let us again check whether we can identify that a particular number is valid in a particular number system. So if we do so, we will be able to understand where is the need for base conversion or converting a particular number from one base to another. Let us check the validity of the same number across different base number systems. Let us see the example in a sequence: binary, octal, decimal and hexadecimal. If I write 100, it is a valid number in binary because it is only using 0 and 1. It is also correct in octal because it can use 0 to 8. Similarly, it is also correct in decimal, 100, and also in hexadecimal. Now if I write 103, this is not a valid number in binary system. Why? Because the digit 3 is not supported in binary system. In binary system only 0 and 1 is supported. So it is not a valid number in binary, but it is valid in octal, decimal and hexadecimal. And we already know the rule why they are valid. If I write 48, it is again not a valid number in binary system. Both the digits 4 and 8 are not available in binary system. Then in case of octal, the digit 4 is available in octal, but the digit 8 is not available in octal system. So it is also not a valid number in octal. But in case of decimal, 4 and 8 are available as digits. In case of hexadecimal also, 4 and 8 are available as digits. So they are valid in these two systems. Now if I write 268B in binary, you can easily understand that this is not a valid for all digits. If I write 268B in octal, for 8 and B, this number becomes invalid because 2 and 6 are valid. So as a whole, the number is invalid in octal. For B, it becomes invalid in decimal. But in case of hexadecimal, 268B is a valid hexadecimal number. So this is how we can identify a particular number in different base, and you can tell whether these are valid to be written in that number system or not. As because we cannot represent 103, which is in octal or decimal or hexadecimal, directly in binary by writing 103, there is a need for converting them from octal to binary or decimal to binary or hexadecimal to binary. So this is the reason why we should learn to change the base of a number system, of a number to another number system. So let us start with conversion of a number which is in decimal system to other systems. The following steps should be performed to convert a decimal, that means a base 10 number, to other base. These other bases could be binary or octal or hexadecimal. The first thing we should do, that we should divide the decimal number by the base of the target system. In this case, if I want to convert a decimal number to a binary number, so the target system is binary. And what is the base of binary or radix of binary? It is 2. So we should divide the decimal number by 2. And we should keep the remainder intact. Next, we should divide the quotient of the division by the base of the target system, which is 2 in our example, and keep the remainder. Now let us go to the third step. The third step is to repeat the step 2 till the quotient becomes 0. And finally, we'll write the remainders in reverse order. So let us see how it is done. The first thing we are going to do is a decimal to binary conversion. So we are converting a decimal number 36 to binary. Target number system is binary. Base of target system is 2. So to convert from decimal to binary, we will divide by 2. Let us take the number 36. Like we factorize, we will divide. So we are dividing 36 by 2. We get 18 as the quotient. And 2 18 is 36. It is perfectly 36. So there is no remainder. Like this, if you keep on dividing, 2 9s are 18, 0 is remainder, 2 4s are 8, 1 is remainder, 2 2s are 4, 0 is remainder, 2 1s are 2, 0 is remainder. Then again, if I divide 1 by 2, 2 1s are, it will be 2, it is more than 1. So we'll multiply 2 with 0. So the quotient will become 0. 2 zeros are 0 and 1 is remainder. Now if we write all these remainders from bottom to top, we'll get the binary of 36, which will be 1 0 0 1 0 0. So the binary of 36 will be 100 100, and the base of the binary is 2. It must be written after the number. Remember, decimal system is the basic system we use in day-to-day life. So for decimal system, we need not have to write the base 10. But for every other system, we need to write the base of the system to indicate that the number is in that particular base. Next conversion will be decimal to octal. Again, we will convert 36 to octal. Target number system is octal. Base of the target system is 8. So to convert from decimal to octal, we will divide by 8. Let us take the number 36. We will divide it by 8. 8 4s are 32. 36 minus 32 is 4. So 4 is remainder. This can be calculated like this also. 8 4s are 32 plus 4 is 36. So if 8 into 4 plus 4 matches 36, we are doing okay. So next we'll try to divide 4 by 8. So 4 is smaller than 8. So 1 time 8 will be 8, which is more than 4. So we'll put 0 times 8. So 8 zeros are 0. And the remainder will be 4. Now again, if we write this from bottom to top, we'll get the octal number. Now the octal number will be 4 and 4, which is 44. And the base of the octal system is 8. So 36 in decimal will be 44 in octal. Next, we are going to convert a decimal number to a hexadecimal number. Let us again convert 36 to hexadecimal. Target number system is hexadecimal. Base of the target system is 16. So to convert from decimal to hexadecimal, we will divide by 16. Let us start. 16 to the 16 to the 32, and the remainder is 4. Again, 2 cannot be divided by 16, so 16 zeros are 0 and 2 is the remainder. As because the quotient is becoming 0, the algorithm is terminated. Now again, if we write all these remainders from bottom to top, we will get the hexadecimal number. So it will be 2 followed by 4, which is 24. So hexadecimal of 36 is 24, and the base of hexadecimal is written after that, which is 16. Let us check one more hexadecimal number conversion from decimal. This time we will be converting 28 to hexadecimal. Target number system is hexadecimal. The base of the target system is 16. So we will divide by 16 to convert from decimal to hexadecimal. Let us take 28. 16 ones are 16, 16 those are 32, it is more than 28, it will go one time. 16 ones are 16, 28 minus 16 is 12, which is the remainder. Now we cannot write 12 because 12 is not a digit, it is a combination of two digits, 1 and 2. So in hexadecimal, as because we write 0 to 15, 0 to 9 can be directly written as digits, but 10 cannot be written as digit. So what I will do, as hexadecimal represents 10 as A, 11 as B, 12 as C, 13 as D, 14 as E, 15 as F. So for 12 we will take the value C. Now 1 cannot be divided by 16, so 16 zeros are 0 and the remainder is 1. So if we write the remainders from bottom to top, we will get 1 and C as the number. So the hexadecimal of 28 is 1C, and the base of the hexadecimal is written after that. So now we will be looking at conversion of other system to decimal. By the term other system, I mean to say that it will be either octal or hexadecimal or binary, from which we will be converting into decimal. The following steps should be performed to convert other base system to decimal system or a base 10 number. First, we need to mark the position of all the digits of the other base system from right to left, starting with 0. Then I have to find the base of the other system number. So if we are converting from binary to decimal, the base of the other system will be 2. That means the number system from which we are going to convert to decimal is called the other system. So for binary, the base will be 2, octal base will be 8, and hexadecimal, the base will be 16. Now we will have to add all the positional digit values calculated as using the following formula, which is digit into base to the power position they occupy. So let us see one example where we are going to convert a binary number to a decimal number. So again we are converting 100 in binary to decimal. So let us find out the target number system, which is decimal. Base of the other system or the given system is the base of the binary, which is 2. So we have to add all the positional digit values calculated as by using this formula, which I have already discussed. Digit into base to the power position. Here we have taken 100 as the number. So let us start to convert from binary to decimal. So this is the number 100. We have marked the position from right to left, starting from 0, as because 6 digits are there, stopping at 5. So I have got the positions of the binary digits. The next step is to use the formula. So we are taking the number or the digit, which is 1, at position 5, which is to be raised to the power of 2. So number is written in blue color, so this is the digit is written in blue color, so this is the digit 1. Base is written in green color, so the base is 2. Here the base of binary is 2, and the position is written in maroon color. So I am fetching 5 from there. So it is the positional value of the digit 1 into base of the binary system, which is 2, to the power 5. Similarly, for the next value it will be 0 into 2 to the power the position, which is 4. For this value it will be 0 into 2 to the power 3, plus for the second position it will be 1 into 2 to the power 2, plus for the position 1 it will be 0 into 2 to the power 1, and for 0th position it will be 0 into 2 to the power 0. Now this is for the first time we are converting binary to decimal. So I am writing all the digits. But remember, for a position where the digit is 0, it will always become 0, no matter whatever may be the power of 2. If I multiply that value with 0, it will become 0. So for next time, I will not consider 0. So it will be 2 to the power 5 is 32 and 2 to the power 2 is 4. Rest of the values are 16, 8, 2 and 1. Now in the next step it will be 32 plus 0 plus 0 plus 4 plus 0 plus 0. 32 plus 4 will be what? 36. So this is the decimal number which is equivalent to binary 100 100. So the decimal of 100 100, which is in binary, is 36. I am just writing the base of the decimal system. I may not write this. The next conversion will be from octal to decimal. So we will be converting 44, which is in octal, to decimal. So target number system is decimal, to which the value is to be converted. Base of the given number system, which is octal, which is 8, will add all the positional digit values calculated as the same formula. Now the number is 44. It is of 2 digits and we are marking them from right to left as 0 and 1. So the calculation will be 4 into 8 to the power 1. Here 4 is the positional value of position 1. 8 is the base of the system, octal system, and 1 is the position, which is raised to the power of 8. Similarly, the next value is digit is 4 and it will be multiplied with base of the octal system, which is 8, raised to the power of the position, which is 0. So the values will be 4 into 8 to the power 1 is 8 and 4 into 8 to the power 0 is 1. If we raise power of any number to 0, it will be what? 1. So it will be 32. 4 into 8 is 32 and 4 into 1 will be 4. So it will be 32 plus 4, 36. So decimal of 44, which is in hexadecimal, will be 36. Now let us again convert a hexadecimal number to a decimal number. So we'll convert hexadecimal 24 to decimal. Target number system is decimal. Base of the given number system is 16. We'll add all the positional digit values calculated as digit into base to the power position. So the number is 24, split it in 2 digits. From right to left they are 4 and 2 and their position is 0 and 1. Now the formula applied like this. 2 is the positional value of the position 1, which is raised to the power, which is multiplied with 16 raised to the power the position of 2, which is 1, plus 4 into 16 to the power 0, which is the position of 4. This calculates to 2 into 16 plus 4 into 1, which is 32 plus 4, and again we get 36, which is the decimal equivalent of hexadecimal 24. So decimal of 24, which is in hexadecimal, is going to be 36. That's all for today. Thank you.